Hello, my name is Xavier Bauder and I'm presenting this work on behalf of my co-authors and especially Monica Hill, who was realizing most of the work in her PhD that is made in collaboration between the University of Basque Country and the Research Center IDEKO in Spain. We are dealing with Aliased beating helix induced by dual frequency vibrations in turning. We are working with machine tool builders and machine tool users that report visual marks on the surface and that need help for making the diagnostics to know what to change in the machine or the process to remove those marks. So we can use vibration measurements to get the frequency contents during the process operation, identify the different components related to bearing failures, auxiliary equipment rotations, for example, but then to know which of those vibrations are causing the surface finish issue is not trivial at all. So, for example, in this use case related to wheel rim, we can see that on the surface we can see the feed per revolution. That is the normal helix that we should get in the turning process, but we have also a long wavelength of 3 mm length that is appearing on the surface. If we look at the frequency spectrum, we have harmonics coming from the spindle speeds, from the belt passing frequency, but in this case, this 9th harmonic of the belt passing frequency that was amplified by a local resonance was causing the problem, and you see that there are many different components, and to identify that this is a problematic one is difficult. So for that, we developed a methodology so that we can analyze both the surface topography and the vibration spectrum to make a proper correlation of the issue in the surface finish. Indeed, we are looking at the frequency contents during the process, and we are also looking at the wavelengths and number of helixes that we get on the part. But to help this diagnostic, we also need simulation and specifically the analytical equations that we could obtain so that we can relate the different frequency components with the wavelengths that will be generated then on the part. And this is helping to make proper correlation and proper identification of the error source that is causing the surface finish problem. To start with a simple process, we started with turning operations. In cylindrical turning with round tooltip, we are looking at waviness issues with long wavelengths, so we are not looking at the roughness problems related to the tool marks, but as the longer profiles of several millimeters. With a normal process, we will get this profile where we get one tool mark every feet per revolution, and we get this turning profile. Then, if we introduce a vibration, what we obtain is a profile that is affected by this vibration, but not exactly linked to the vibration, but to the Aliased vibration because of this process that is sampling the profile once per revolution. And then what we see is not the wavelength related to the vibration itself, but to the Aliased vibration with this Aliased wavelength. And this is clear in the surface topography where we can see this helix generated by the Aliased vibration with a wavelength that is marked here in blue. So then, if we look at this problem, even if it seems simple at first view, it's a turning process with only one single vibration, it's getting more complex than what expected. Because with low vibration, what we get is the tool field marks, and in the background we have a secondary helix related to the Aliased vibration. So this was well known for lots of time. Then, if we increase the amplitude of vibration, keeping the same frequency, the Aliased vibration is becoming dominant. The tool field marks are not clearly appearing in the part, but in the background we have one sub-Nyquist artifacts that are appearing related to a secondary patterns of surface marks. For the sub-Nyquist, what's happening is that we have the tool motion that is sampled once per revolution, but this sampling in some situation can lead to this effect where you see that we can describe them by 3 interlaced waves, and this has been studied mathematically by Amitro and been seen in milling by Grossi, but was not clearly detailed for turning operations. And so what's happening is that on the surface we see the sub-Nyquist marks that are dominant, and in the background the Aliased helix that is still present. So thanks to this work, we could define that the important parameter is the frequency ratio between the tool vibration and the workpiece rotation frequency, and that this frequency ratio is divided in an integral part and decimal part, with the decimal part epsilon that goes from -0.5 to 0.5. And indeed, we can have two different profiles that are exactly the same with two different frequency ratio, because what is important is not the frequency ratio, it's the decimal part of the frequency ratio when we're looking only at one profile. And you see that here we have a decimal part that is 0.48, and that it's leaving the same wavelengths on the part and the same frequency content when we are looking at the wavelengths at the FFT of this axial profile. What is modified by the sign of epsilon and by the integral part of the frequency ratio is the number of helix that we get related to the integral part and the direction of those helixes that are linked to the sign of the decimal part. So to make a proper diagnostic, it's important not only to look at the external profiles, but to look at the number and orientation of the helixes that are present in the surface. Then, thanks to this work, we could get to this table with the different equations for wavelengths, number of helix and helix orientation, depending on the situation. If we have the tool feed, we have one mark per revolution, so one helix, that is considered as positive orientation. Then the Aliased vibration, that will have a wavelength that depends on the inverse of the decimal part of the frequency ratio, number of helix related to the integral part, and the sign will be given by the sign of epsilon. And then the sub-Nyquist artifacts that will appear depending on the integral part, decimal part, and also on some sub-Nyquist ratios that are defined. And with this, we can get this kind of maps where we have the frequency ratio, the amplitudes of the vibration, and depending on where we are, the dominant helix is changing. So with this, it doesn't mean so always on the surface we have more than one helix, but the dominant one is defined by these equations and this map. And now, what's happening when we have two vibration frequencies? So there are previous publications reporting the beating effect that appears when we have two frequencies that are next to each other and with similar amplitudes. In this case, it was a grinding process with dressing that was considered, with rotations from the grinding wheel and from the dressing wheel. And as we have two frequencies that are next to each other, we will have these long wavelengths of beating, and the wavelengths of the beating will be related to the distance between omega-1 and omega-2. And this can also leave marks on the surfaces. However, if we have two vibrations that are related, that are next to each other, but one of them is harmonic of the workpiece rotation, then we can have the tool motion that has a clear beating, but after aliasing, considering the sampling from the process, what we have is only a sine wave related to the aliased wavelengths of the element that is not harmonic of the workpiece rotation. So it means that it's not because we see that the tool motion is beating that we will have beating effect on the workpiece surface. Indeed, if we have an harmonic vibration, this harmonic vibration doesn't generate an helix. It generates an offset on each profile, and so this means that we will have 4 mirrors on the workpiece. In this case, the integral part of the frequency ratio is 3, so we will have 3 lobes on the workpiece, but each profile is the perfect profile obtained for a perfect turning process. Then, if we have one vibration that is not harmonic, we will have the wavelengths coming from the Aliased vibration in this case of some Nyquist, and this will leave marks. And if we have the combinations of both, what we get is the offset plus the sine wave. But on the profile and on the topography, what we get is the effect of the frequency that is not harmonic of the workpiece rotation added to a 4 mirror on the workpiece related to the harmonic vibration. Another important element to consider is that two faraway frequencies can beat once they are aliased, because what is important in the beating, it's not the distance between the frequencies themselves, but the distance between the decimal parts of those frequency ratios. Indeed, in this case, we have a decimal part of 0.34 and the one 0.39, so they are nearby each other, and we see clear beating on the Aliased motion with this lambda p wavelength. And this is causing issues on the surface, and we'll have this dominant helix that is coming from the beating between two frequencies that are far away, but that have similar frequency ratio. And again, in this situation, you can have exactly the same profiles with different combinations of frequencies, because the one axial profile is linked only to the decimal parts of the vibrations. Then the integral part and the sign will again have an influence on the direction of the helix and on the number of helixes that we get in the part. So in this paper, we could define the equations to get the adimensional parameters that are important to analyze this problem. So we define the Aliased motion as a sum of two sine wave components, and then we wrote those equations to clearly identify what is coming from the envelope of the beating and what is the inner wave modulation that we get inside of this beating. The envelope is linked to the epsilon p and lambda p, that is the wavelength of the enveloped beating that is related to epsilon p, with epsilon p the frequency ratio of the decimal part of the frequency ratio of the Aliased envelope frequency ratio. So we get those non-dimensional parameters. For the single frequency, we add the frequency ratio 1 and 2 that is divided between the integral part and decimal part. And for dual frequency vibration, what we add is a new frequency ratio that will be the addition or subtraction of those previous ratios, depending on the sign of the multiplication of epsilon 1 times epsilon 2. And with this, we get a new frequency ratio, Cp, that is again divided in integral part and decimal part, that will explain what are the number of waves and wavelengths obtained on the surface because of this beating between two frequencies. So what we get is a new line in the table with analytical equations giving the wavelengths that is dependent only on epsilon p, so only on the decimal parts of the two vibrations that we're considering, and the number of threads that is depending on the integral part. And like this, when we look at the topography, we can make measurements axially and in a circular direction to know what are the wavelengths and what are the wave numbers. And we have analytical equations that are related to each peak that we see on the wavelength spectrum. We can see in this case that we have elements that are coming from the aliasing vibration of the second component. From the first component, we can see the vibration coming from the inner waves of the beating, from the outer waves of the beating, and also from some Nyquist artifacts of the second vibration. And like this, we can make a proper identification of all the components and their related frequency issue that is causing these marks. So those results have been validated experimentally. We are using aluminum workpiece to minimize the wear issue and to have a clean cut. We are using a piezoelectric actuator below the tool so that we can impose a given frequency and amplitude vibration so that this vibration will be dominant and clearly mark the workpiece surface. Then the metrology is done with contact measurements where we can scan the part so that to obtain those surface topography maps. You see that we have a very good match between the simulated topographies and the measured topography. In the measurements, we have an additional effects coming from the runouts that is giving a form error, but the number of helix and wavelengths are matching perfectly. So to conclude, and to see what is the further work, the first conclusion is that we can have two nearby frequencies that can beat, but it doesn't mean that it will generate a wavy surface, especially in the case where we have one of those frequencies that is harmonic of the workpiece rotation. Then the other interesting findings that we can have two faraway frequencies that can beat due to the aliasing effect. And what is important to consider is not the frequency itself, but the decimal part of the frequency ratio. and this will define the wavelengths and the beating effects that will appear on the surface. As a further work, we would like to continue developing a diagnostic methodology that will consider the measurements limitations and uncertainties that we have. Very often we can measure a limited length on the workpiece, so we have uncertainty on the wavelengths, and this will cause uncertainty in the determination of the frequencies that can cause a problem. And also we would like to know what is the adequate or optimum measurement strategy to know which parameters should be obtained from the surface to make a proper diagnostic. Then we would also like to extend this work to grinding applications, especially to plunge grinding, because during the dressing process we can generate marks, and the kinematics of the dressing process is exactly the same as the one that we are considering here in turning. Then the grinding wheel can have those marks, and they are copied to the surface that is ground. So what we like to do is to analyze the ground surface and be able to detect what is the problematic vibration in the machine that is causing surface finish issues. So thank you very much for your attention, and I will be pleased to answer your questions.